Yeah. So just a brief intro. So we all know that if you supercool a liquid, then the relaxation time increases very rapidly as you supercool without any significant structural change, and that you can see in this plot. So this is the plot of the relaxation time or the viscosity as a function of 1 over temperature, and with a very little change in temperature, the viscosity actually grows by 7 orders of magnitude. And the origin of this slowdown, this slowdown of dynamics with increasing temperature or decreasing temperature or increasing density is still debated for real glasses. But we know what happens in the limit d going to infinity or in the main field description, and this is a very rough schematic of that. So at high temperature you have a liquid and the configuration space is well connected. You can sample all the configurations, and as you supercool you start to form this island connected by these thin paths, and the system spends a lot of time in this island, and once in a while it goes to the other island, and there exists this mode coupling transition or this dynamical transition where you actually this island gets disconnected and the time scale diverges. Okay, so that is the dynamical transition, and so these are the amorphous or glassy state, and once you are within one of this island, you never come out of that. So you are stuck there forever. So you just rattle around. Okay. So physically, what happens is that every particle in the mean field limit is caged by all the other particles, and it is not able to break the cages. Okay. So this is what happens at the mean field level. Now, as you can see that this dynamical transition is actually the limit of stability of this metastable glassy state. So it's actually a spinodal, and it is found to be in the same universality class as the spinodal of the random field Ising model. Now, as Bhavtosh talked about it yesterday, so if you have a spinodal, you have this critical scalings, and from the mean field theory, we know that if you look at the cage size, then this cage size will follow a square root scaling with density. So I'll define the cage size shortly. So this is the cage size at the dynamical transition minus the cage size at a density above the dynamical transition, and its scale as phi minus phi d to the power half. And along with that, there is also existence of this upper critical dimension for the spinodal, which is d equals to 8. Okay. Now what happens in, one more thing. So the spinodals are actually quite universal. So you see this kind of spinodals in different contexts ranging from magnetic system to mesoporous materials to social sciences. But they're very difficult to study in finite dimension, and I'm going to explain why. So the first thing is that when you go to finite dimension, there is no, as Sarika explained, there is no criticality, there is no formal dynamical transition, there is no divergence. Okay, and the reason is that in finite dimensions, these particles are not perfectly caged, so they can undergo these activated processes and they can break the cages. Okay, but still, as Sarika again explained, you can extract this. So for her it was TC. So for me it is phi d. So d c is replaced by d. Okay, so you can still fit this power law scaling, and you can extract a dynamical transition density for this avoided dynamical transition in finite dimension. Okay. Now, if you look at the plot of mean square displacement as a function of time, so this red curve corresponds to the case when you have a perfect caging in, let's say, in the mean field limit. So at phi d, you have a perfect caging, and this plateau will never end. But in finite dimension, even above phi d, where things should be caged, you have you have a plateau up to certain time scale. Then it shows the diffusive regime. So things relax even beyond phi d due to this activated processes. Okay. Now this is the way I would define the cage size, which is the plateau height of this mean square displacement. Okay. Now so this is the main difference between the infinite dimensional solution and the finite d picture. And there is also one more thing, again Sarika explained, that so the dynamics is definitely much more complex in finite d, and also the structure of the liquid is also complex in finite d. For example, if you look at different dimensions, and if you look at the pair correlation function, G of R has this nice solvation cells, and if you increase your dimension, you start to see that these things go away, and in the limit of d going to infinity for hard sphere you have a step function. Okay, so there is no structure in the liquid, so that's why the limit of d going to infinity is solvable, because it has no structure. Okay, so as you already guessed, that this spinodal that exists in this mean field limit actually doesn't formally exist in finite dimensions, and the fluctuations actually destabilize this glassy states much before you actually reach this spinodal. Okay, now the question we want to ask is that, so we want to play a game, and we want to, so it's a gamble. So you want to ask whether there is any remnant of this spinodal criticality in finite dimension. Okay, so whether you can get any Paul law, and if you get, how will it look like? Okay, now as I explained to you that so to get this scaling, you have to go beyond phi d, which is again a difficult task. For example, if you look at if you do it with a normal Monte Carlo or normal molecular dynamics, you can barely simulate up to phi d. So you have to go beyond phi d and look at the scaling. Okay. Now, luckily, recently it has been shown that if you take a continuously polydispersed system, and if you design something called a swap Monte Carlo, where you choose two spheres randomly of different radii, but they have to be roughly equal in size, and you swap or you interchange the diameter of these two spheres. Okay, and that seems to be very effective in thermalizing the system much beyond the dynamical transition. And the reason is that you are just bypassing this sluggishness by sampling the configuration space very efficiently, but avoiding fractionation on fractionation. Okay, so you don't want to crystallize your sample, so you want to stay in the reciprocal liquid phase. So that's the challenge. So what you ultimately do is that you tailor your system such that the efficiency of the swap move is maximal, but at the same time you do not want to crystallize your system. Okay, so this is the plot for the relaxation time tau alpha as a function of pressure or density, and this is the curve for the standard Monte Carlo, and this is the curve for the swap Monte Carlo, and you can see that, and this is actually the limit up to which you can simulate roughly, and this vertical line corresponds to phi d or zd. Now you can see that for the swap Monte Carlo at phi d the relaxation time is very short, and you can actually, with swap Monte Carlo, you can thermalize systems much above this experimental glass transition temperature or the glass transition density. So this was the success of swap Monte Carlo, and so what we did was so we optimized this swap Monte Carlo in higher dimensions. So I looked at I started from d equals to 3 and went up to 8 and 9 dimension, and I optimized this swap Monte Carlo, and here is the plot for okay, so I have to explain what is phi d swap. So as we can see here, that phi d is sort of the limit up to which you can simulate using a particular dynamics. So for normal dynamics I have a phi d, which is this, and for swap also I have a phi d, but it is pushed up to a very high density, right. So when swap is working, that means there is a gap between this phi d swap and a phi d standard dynamic. So if the gap is 0, that means swap is not effective at all. So I have plotted this gap. So this is the difference between the phi d swap, which is somewhere here, and this is the phi d standard as a function of polydispersity, and the polydispersity is just the width of your distribution, particle size distribution. Okay, and this is the plot for that for different dimensions. So it increases at first and then saturates beyond a certain polydispersity. But the important point is that this plateau height actually goes down with increasing dimension. So which implies that with increasing dimension the swap efficiency actually goes down, and it goes as 1 over d, but it remains reasonable up to d equals to 8 or d equals to 9. So the idea is that we can still use this swap Monte Carlo to thermalize systems in high dimensions, and with that we can actually achieve deeply supercooled liquid configurations, and we can do some static computation, we can verify mean field predictions and study the low temperature physics. So I'm going to use this tool to study high dimensional systems, and I want to look at the cage size now. Okay. So as I explained to you that even above phi d in finite dimensions, there will be some diffusive regime. So this is a mean square displacement. So there is no clear plateau, and these are the density is above phi d, and you can see that you can get a clear plateau only when you go much above phi d, right. So I want to look at the histogram of this plateau heights. So that's so for that, because there is no clear plateau, so I have to define a time scale for that, right. So I define the time scale using this non-Gaussian parameter alpha 2, which has a peak around tau alpha. It's somewhere here. So I have to define a time window, and I fix the upper bound of this time window as a time when when we reach 20% of this peak of this non-Gaussian. So it's kind of ad hoc. You can do 10% also. So I just want to sort of capture maybe. So if you look at this curve, I want to maybe look at this within this window where it seems to be little more or less flat. Okay. And the lower bound could be like when alpha 2 starts to depart from this plateau, but it does not matter because this time is much larger than this time. Okay. So this is my protocol. So I am going to look at a fixed time window, and I am going to look at the histogram of this plateau height, and I am going to look at the, I want to calculate the average, the typical case size. Okay. And this is my case size, this plateau height. So this is how the distribution of this case size look like. So as you see that so it's true for all dimensions. As you increase your density, the peak or the mode of the distribution shifts to the left. That means the cage size becomes smaller as you increase the density. So cages become tighter and tighter. And we define the typical cage size as the mode of this distribution. Okay. And now we can finally calculate look at the critical scaling. So I want to look at how this mode change scales with density or the packing fraction. Okay. So this is the data for starting from 3 up to 9. This is the power law scaling for delta phi d minus delta phi as a function of phi minus phi d. So, for 3D, yeah, I'll be done soon. So for 3D, we get an exponent of 0.7 roughly, and as we approach this upper critical dimension, we see that the exponent actually goes to this mean field value of 0.5. So the main, there are like two main results. One is that the mean field criticality softens as you lower the dimension, and we actually we can verify the existence of this upper critical dimension. So beyond 8, it sort of goes to a mean field value, but there is big error bars. The last thing I just want to do in 1 minute is that, so high D simulations are very tough because you need to you can barely simulate like 1 or 2 particle size in the linear dimension of your box. So because like to simulate a bigger to simulate it reasonably well, you have to take a large number of particles. So there's one way to avoid this problem. You change, so this squares corresponds to my simulation box. So if you take a cubic periodic boundary constant, it means that you are considering a cubic or hypercubic lattice of your simulation boxes, and the image distance, so the distance between the particle and this image is actually quite small, which is L for the cubic lattice. Now if you change the box shape, you can actually increase the image distance. So if you cleverly choose your box shape, then you can sort of get the same length scale with a smaller number of particles. So we chose a lattice called a DD lattice, and I can explain it later offline. So for DD lattice, so it's harder to compute the image in this DD lattice. So that actually competes with the efficiency gain in lower dimensions. But if you go to high dimensions, it becomes very, very efficient, and it goes as 2 per d minus 2 by 2. So in high D, it's huge. So this actually led us to simulate up to 17 dimension. So this is just like fun figure. So this is the equation of state for high dimensional hard spheres. And yeah, I just want to conclude at that point. So this work was done with Ludovic and Patrick, and I want to thank the Simons Foundation. So 17 is the new infinity. Thank you.